Hello class, how's it going? It's Sunday morning. I'm recording what was this? Oh, that's why I was doing that. This didn't look like Cal 2. This crazy quadratic formula junk. How's it going? Today is, I think, the last day of lecture for exam 3. After this, I'll be posting the practice exam and then eventually doing the practice exam. It's Sunday morning. I'm recording this at a weird time because I'm running errands all day tomorrow. I didn't send you guys a text because nobody's been watching live anyway, and it should be around tomorrow at the usual time to watch not live. We got 2 more topics to talk about for exam 3. Let's hit it. The first one is called is about solids of revolution. Volumes of revolution. That's what the section in the book would be called. A volume of revolution is the solid volts when a 2-dimensional region is revolved about some line. What does that mean? This is one of these definitions that I write a thing down, but you still don't understand what it means at all without a picture. Suppose I take this rectangle. I got a 2-dimensional rectangle. I'm going to revolve it about the y-axis. So that means every point in that rectangle is getting replaced with a circle getting swept around the y-axis. If I take the union of all of those circles that are resulting from all of those points being swept around the y-axis, what do I end up with? You imagine this for a second. You end up with a cylinder. That's a terrible drawing of a cylinder. Let me try this again. Yeah, something like that. If you have the same book that I used to teach out of, there's a good chance that your textbook has like a full chapter or like a subject of a chapter about drawing good drawings in 3D planes. Drawing 3D drawings mathematically good is hard. You learn a bunch of little tricks, like how I didn't connect the lines behind the y-axis here to indicate that that part of the circle is behind the y-axis. I added a dotted line partway through to show what a cross-section looks like. I didn't assign any homework about stuff like that, but that's probably something worth looking and seeing if the calculus textbook you own has. If I take a triangle and revolve that about the y-axis, what will I get? Well, if my triangle is leaning against the y-axis anyway, I will get a cone. I can take a circle, or I guess to me it feels better to take half a circle, because otherwise I'll hit everything twice, which I don't need to. I revolve that about the y-axis. What do you get? You get a sphere. And the thing we'd like to know is how do we find the volumes of these shapes? There's a more general principle that you're going to use a bunch in Cal 3. We're not going to hit it hard here. And the idea is when you're trying to find areas in regular calculus, you think about what is the cross-section at a different point. The cross-section is always going to be a line segment. You take the length of that line segment, and the total area is the integral of that length from somewhere to somewhere, right? Integrating the one-dimensional cross-section of the area gives you the total area of the thing. And this extends to 2 dimensions and 3 dimensions in the way that you might expect, where if I draw a 2-dimensional shape, and ask for different x values. So here's a three-dimensional shape. And I'm going to say for each x value, imagine the cross-section. If I take this cone, my two-dimensional cross-section in this axis will be a, I think that's a parabola? It might be a hyperbola. Yeah, if I did it at an angle, it would be... Okay, so you get this hyperbola shape. And you let a of x be the area of that cross-section for every x. Then, the total volume of the entire cone is going to be the integral from a to b, whatever the endpoints of the cross-section are. When does the cross-section first exist? When does it stop existing? Of what is the area of that cross-section. The volume is, in general, the integral of the area of the cross-section. There's a couple details. You need to make sure that your cross-sections are perpendicular to the axis that you're integrating on. If you integrate this at an angle, then you're going to be stretching out the axis. So don't do that. But this is the general thing. Like, this needs to be a right angle here. Same deal here. This needs to be at a right angle of the axis that you're integrating against. If you want to integrate it at an angle, that's fine, but you need to fix by some constant. This is stuff that you think about much harder in Cal 3 than you think about here. And in general, how do you find this area? It's very likely to be its own integral to work out. In Cal 2, we don't do the versions where there are harder integrals inside of the integral to work out. We're going to do the simple versions where we know how to find the cross-section. And the key thing here is for Cal 2, we're not going to try and integrate the cone like that. We're going to lay the cone on its side and integrate against these cross-sections where I already know a formula for finding the area. My area is in general going to be a circle or a circle with a circle cut out of it or something like that. It's going to be pi r squared or pi r squared minus pi little r squared if there's a hole inside the region. Let's try doing this. Can I come up with a good example? Well, I don't need to come up with a good example. I have these notes right here. Don't forget you have notes right here, Andy. I guess let's write the formula out. The general thing going on here is if I have some blobby shape and I'm revolving around the x-axis, then there are two possibilities for my cross-section. Either my cross-section was a stick before the revolution. Wait, this is a bad picture. Say this region is getting revolved about the x-axis. I think about a cross-section. My cross-section might be a stick, in which case my new revolution volume is the area of a circle. The typical way to think about this is instead of doing a stick, I take a stick with some thickness. I have some delta x value. Is my differential that's going to turn into a dx when my thing turns into an integral. My cross-section is now being approximated by this thing called a disk. The actual shape is not quite a disk because this thing has like some kind of angle to it up here. So I've got some kind of weird non-disk thing where it's like skinnier at one end and wider at the other. But just like with a regular integral, those differences, this area is still well approximated by the stick. This disk-like thing is pretty well approximated by this disk. It's close enough for the integral to work out. Something about the mean value theorem makes this work. Adding these up, so the volume of this disk is pi r of x squared delta x. Adding those up, becomes an integral, pi r of x squared dx. That's one possibility. The other possibility is I have a stick that's not adjacent to the x-axis. When I revolve that around the x-axis, we get what's called a washer, which is a disk with like a plumbing type washer. Or I guess it's not just plumbing, but the kind you stick between a screw and a bolt to prevent friction between the bolt and the whatever. I guess it's not about preventing friction, it's about diffusing the pressure so that pushing against it doesn't slowly unscrew the bolt over time or something like that. So this is called a washer. And this is called a disc. And this formula is called the disc method. And the version with a washer is the same formula, but we've got two radii now. We've got a little r and a big R. And the volume of this washer is pi big R squared minus pi little r squared. And the total volume of the thing is going to be the integral from somewhere to somewhere of pi. You usually factor the pi out. Big R squared minus little r squared. Right? Okay, let's try this out. Let's find the volume of a sphere of radius 3. 3? Yeah. How am I going to represent this? Using the washer method. The disc/washer method. So I'm going to describe the sphere of radius 3 as taking half a circle and revolving it about the y-axis. So that's the picture I made a second ago. I'm going to care about what is this shape. This shape is x squared plus y squared equals 3 squared. 3 squared is 9. That's the shape of the region that's going to get revolved around the y-axis. People draw these little twirly arrows to say this is the axis we're revolving around. And the thing I want to now think about is, what does my typical cross-section look like? One of the things that people mess up on in these problems is, am I about to do an integral with respect to x or an integral with respect to y? The thing I want to imagine is taking one of these little sticks. To specify a stick, am I picking an x value or a y value? I am picking a y value. Why did I draw my stick going horizontally instead of vertically? Because I want to think about sweeping this stick around the y-axis, and I'm hoping to end up with a disc or washer. If I drew a vertical stick, which we will do problems like that in a second, my shape ends up being like a can or a cylinder. I guess they call this a shell. That is the wrong shape. I want a disc or a washer. I need a horizontal stick to sweep out or revolve around the y-axis. Okay, I see that I have my disc. I specify my disc by picking a y value. To catch all y values, to catch all of these discs and stack them up and build a sphere, I need to let y go from -3 to 3. This is what's telling me my bounds of integration. To catch all of these sticks, the y value that I picked at the start needs to range from down to y at y equals -3 up to y equals +3. I guess I don't really need it to hit -3 and hit +3 because those are size 0, but you go all the way up there. The thing I'm integrating is going to be pi r of x squared, not r of x, r of y squared, because this is going to be a y integral. How do I find what this radius is going to be? Here's where I use the equation. My equation tells me x squared plus y squared equals 9. My radius is this distance. It is the distance between x equals 0 and x equals whatever that x value equals. This x equals some function of y. I want to take that equation and solve it for x. X squared plus y squared equals 9. X squared equals 9 minus y squared. So x is plus or minus the square root of 9 minus y squared. I've drawn it to the right of the y-axis, so it's the positive version. My formula is x equals 9 minus y squared. Is the square root of 9 minus y squared. Is the formula for what this distance is as a function of y. It's going to be a function of y because I'm integrating the thing with respect to y. It's going to be a function of y because for different y values, the stick is going to have different lengths. So I've got my radius, r of y, is the square root of 9 minus y squared, which comes from what was the equation of the surface to begin with. And now I have a thing to stick in there. Oh, I forgot the squared. It's pi r squared is the radius. We get the integral from -3 to 3 of pi radius squared, where radius is root 9 minus y squared dy. I don't know if you've done problems where you integrate with respect to y instead of with respect to x. I remember that really threw me off for a while. But, you know, it's the exact same principle of integration. Nothing's changed. It's just a different symbol there. I need to pi integral -3 to 3, 9 minus y squared. I would often say now you just do the integral and there's nothing interesting left, and you know how to do integrals already. But this one's easy enough, I'll do it. I get pi, the integral of 9 is 9y, integral of y squared is 1/3 y cubed. I need to evaluate this from -3 to 3. Plug in 3, I get 27, minus 1/3 of 27 is 9. Minus, now plug in -3, I get -27, minus -1/3 of -27 is 9. 27 minus 9 is 18. I'm getting 18 minus -18. 18 plus 18 is 36. I'm getting 36 pi. Hooray! Is this right? The volume of a sphere, the formula is 4/3 pi r cubed. Our sphere has a radius of 3, so 4/3 pi times 3 cubed. It's 27. Divided by 3 is 9. 4 times pi times 9 is... Yay! I got what we were supposed to get. Hooray! There's sort of a weird thing that happens here, where I feel like I have just verified that the integral process works correctly, but in the way more abstract sense, some geometry teacher told you the volume of a sphere is 4/3 pi r cubed, but never actually proved it. We just proved that the volume is 4/3 pi r cubed. It's not like we checked our work on the right, we checked our work on the left. This is the thing that didn't have justification before, and now we've justified it. Hooray! That's volume of a sphere. Many of them are this easy. Let's do one that's harder. Because it has a weird phase shift thing going on. Let's think about the region above the axis. So, here's a pain, because the way they explain these things can be a pain. The region above the x-axis, bounded by y equals x minus 2, and y equals square root x, and y equals 0, is revolved about the line y equals -2. What's the volume? We got a couple things that are a pain here. One, we got to figure out what this region is. In general, the expression the region bounded by, okay, so bounded, a shape is bounded, means you can draw a circle around it. It doesn't spiral out to infinity in some direction. We found the areas of some unbounded regions when we talked about improper integrals. But in general, if we're doing calculus, we're usually trying to do it on a bounded region. If I draw all these lines, y equals x minus 2, that looks like this. Y equals square root x, that looks like this. The x-axis looks like this. How many lines have we cut the plane into? We have this region, 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 we have this region. The instructions say the bounded region. Only one of these 6 regions is bounded. Also, only one of them... I guess the only bounded one is above the x-axis. Those lines weren't even necessary. There's only one bounded region cut by those 3 curves, and it is this one. So that is the region that we were talking about. I probably care about what are the endpoints of this region. The line y equals x minus 2 has its x-intercept at 2, 0. The square root of x intersects the x-axis at 0, 0. The line x minus 2, where do you intersect root x? Square both sides, x minus 2 squared equals x. X squared minus 4x plus 4 equals x. X squared minus 5x plus 4 equals 0. Minus 5 plus 1? What? That's not right. Oh, minus 4 minus 1. Yeah. X equals 4 and 1. Is this right? Okay, yeah, this is right. We got these two intersection points. This always throws me off. One of them is extraneous, is coming from those lines would have crossed if we had the entire square root thing here. That's happening because we squared both sides of the equation, is losing the fact that we only want to talk about the positive square roots. So that one's not actually a solution. The one that is a solution is over here at x equals 4. This point is 4, 2. Square root of 4 equals 2. 4 minus 2 equals 2. They are both, this point is on both curves. This is the region. Two things are making this a pain. One, instead of revolving around the x-axis, we're revolving about the line y equals negative 2. So we're increasing our radius by some amount. That's not so bad. It's just going to change how we work out the radius. Isn't going to be the distance from here to 0. It's the distance from here to negative 2. Not too tough to deal with. The thing that's a bigger pain is I have two clearly distinct types of cross-section. Here, if I think about my cross-section sweeping left to right, I want to think about a vertical stick sweeping left to right. That's the thing that's going to give me a washer. Some of the time, my washer extends from up here at y equals root x down to this line y equals 0. Some of my cross sections, though, after I pass a certain point, are going to extend from the top y equals root x to this bottom y equals x minus 2. There's a phase shift that happens. For part of the integrating region, this is the top, this is the bottom. For another part of the integrating region, this other thing is the bottom. It still has the same top. So we're going to have to split this up into two separate integrals. I guess I could technically define my bottom function of x to be a piecewise defined function, to be 0 if x is less than or equal to between 0 and, 2? And x minus 2 if x is between 2 and 4. And now use that function to integrate, but if I'm integrating it in pieces, I might as well just cut the whole integral into two pieces. This piecewise defined function thing seems like a hassle to think about. So what's going on? Between x equals 0 and x equals 2, I still have a washer. My outer radius is going to be the distance from here to the center of my, I guess maybe I never drew my region. What's my region going to look like? I'm going to have a reflected copy of that thing. I should draw my region somewhere else because it's going to ruin that picture. I got this goofy shape. I got my reflected version of the goofy shape down here at negative 4 because I went across x equals 2. So I want to imagine like this and this and this. It's going to be like something like that. Yeah, I have a hard time. I think I can kind of imagine this thing. I can't think of an object that has this shape, but it's like a piece of a cone that's sort of bendy on the outside and flat on the inside. Oh, and I'm losing track of this part. I didn't get this part. Okay, so if I stood it up, it would look like that. So I wouldn't be able to see if I stand it up, I can't, this is going to be vertical parts down. I'm not going to see the part on the inside where it switches over to being outery. I don't know, it looks like maybe if I stuck a cylinder on top of it, this would be like the bottom of a rocket or something, I don't know. That's the shape I'm trying to imagine figuring out the volume of. Okay, on x equals 0 to 2, my outer radius is what, and my inner radius is what? My outer radius is going to be the distance from negative 2 up to this top function is root x. So I'm thinking about what's the distance between root x and negative 2. That'll be root x minus negative 2. Cool? Cool. My inner radius is going to be what's the distance between here and here. So what's the distance between 0 and negative 2? Well, that one's easier. It's always 2. My inner radius doesn't change as my vertical stick shifts left to right. As I slide my x value left to right, my inner radius doesn't change. It's flat. So I'm getting a constant here, which is fine. My outer radius does change according to the function root x. So this chunk is going to be the integral from 0 to 2 of pi big radius squared minus little radius squared dx. That's going to give me this part of my volume. Plus, now I want to know what's this part of the volume. The same deal for the outer radius. Now I'm picking an x value between 2 and 4. So that's going to be this part of the integral. Between 0 and 4, I use this other slightly different version of the formula. Pi. My outer radius is going to be the same thing it was. Let's draw a specific blue stick to think about. This radius is still the distance between root x and negative 2 is root x plus 2. This inner radius now is the distance between y equals x minus 2 and y equals negative 2. So my little r of x is going to be x minus 2 minus negative 2. Oh, the minus 2's cancel. That's convenient? Is that convenient? I don't know if that's good or bad. So it's pi big radius squared minus little radius squared is root x plus 2 squared minus little radius is x minus 2 plus 2 is just x squared. Is this okay? This is, why did I ask that? There's nobody talking back to me. This is how you set this up. There's kind of other ways to get at it. You could think about, well, I'm just not going to cut that middle part out. I'm just going to think about this thing revolved around that line minus this thing revolved around the line. This is a thing you can set up without the phase shift. This is a thing you can set up without the phase shift. So you can set it up as those two integrals, one minus the other. It's not particularly easier because it's still two different versions of the integral that you're adding together. But that's another way of thinking about it. If that's the more natural way for you to get at it, that works too. They're both still the washer method. And, did I write this wrong? This is supposed to be the integral from 2 to 4. 2 is the place where we start using the other phase shift. Should I do this integral? Yeah, let's do this integral. Doing the integral is usually not the interesting part. I guess in theory this would have happened before we were very good at integrals back in exam 1. This could have been the first thing we talked about in the year. Integral from 0 to 2, what do you get when you square this? Square the first part, 2 cross term. Square the second part, minus that thing. Oh, those cancel. Plus pi times the integral from 2 to 4. Foil this out, you get x plus... Oh, I didn't double the cross term before. That was supposed to be 4 root x. 4 root x plus 4 minus x squared here. Yeah, you just integrate this. Pi times integral of x is half x squared. Oh, that was supposed to be root x, not root 2. That's 4x to the 1/2. The integral of x to the 1/2 is x to the 3/2. With a 2/3 out front on the 4, that'll be 8/3. I need to evaluate this from 0 to 2. Ah, gross, there's going to be root 2's in our answer. What's this integral? Half x squared. X to the 3/2 with a 2/3 out front makes 8/3. 4x minus 1/3 x cubed. Evaluate that from 2 to 4. I wouldn't go through all this work, but we're about to do the same volume using the second method, and I want to confirm that we get the same answer both ways. That gives me warm feelings inside. Plug in 2. I get pi times 1/2 2 squared is half of 4 is 2. 8/3 of 2 to the 3/2 is 2 root 2. Okay. Minus 0, plugging in 0 to those things does actually give you 0. Make sure you remember to think about that. Plugging 0 into everything doesn't always give you 0. Gross, now I need to plug 4 into this junk. 4 squared over 2 is half of 16 is 8. 8/3 of, plug in 4. Oh, I can do the square root of 4. I get 2 cubed is 8. 8/3 of 8. 4 times 4 is 16. 1/3 of 4 cubed is 64 over 3. Minus, let's plug 2 into all this stuff. Half 2 squared is 2. 8/3, 2 root 2. Ooh, this is going to cancel with the other 8/3, 2 root 2. That's great. The root 2's go away. Plus, 4 times 2 is 8. Minus 8/3. Close that, close that. Okay, this really does go away. This is 8/3, 2 root 2 pi. This is minus 8/3, 2 root 2 pi. Cancels. Awesome. What's left then? I get 2 pi plus everything else inside is just a regular number, right? 8/3 of 8 is 64/3, cancels with that 64/3. 24 minus 2 is 22, minus 8 is 14. So I get 14 pi minus 8/3 pi. Is this going right? Let me just stare at this for a second. Oh, I can do this. That positive 8 cancels with that negative 8. 16 minus 2 is 14, yes. Minus, oh, this has a minus on the negative 8/3, so that should be positive 8/3 here. So I got 16 pi plus 8/3 pi. What's 16 plus 8/3? 16 times 3 is 48. Plus 8 is 56 pi over 3. Let me see if that's what I got in my notes. It is! Hooray! Cool. So that's one way of doing this. That's the disk washer method. It takes me a lot of effort to spell disk with a K, because compact disk doesn't spell it that way. It's like the only disk I ever look at. A digital versatile disk is also spelled with a C, I think. That's the disk washer method. Okay, that's one way of doing this. The other way of doing the same technique, let's picture revolving this around the, let's make it a simpler shape. There's no reason for me to make a complicated shape. Let's just take a rectangle and imagine revolving it around the y-axis. The disk washer method would have us take a horizontal disk and picture revolving that around the y-axis. So our shape is a disk, or possibly a disk with a hole in it that we're calling a washer. About the y-axis, or an avertical line, you get an integral with respect to y. You start with a horizontal stick. Sweeping that around a vertical axis will give you a disk or washer. You end up integrating something with respect to y. I want to think about the same rectangle revolved around the same axis, but I want to think about what would I be doing if I started with a vertical stick. To catch all of these vertical sticks, I will end up considering x going from somewhere to somewhere. We'll end up with an integral with respect to x. What are we going to end up integrating with respect to x? Well, the source of our formula came from, think about a disk with some thickness. The thickness will be the dx part. Sweep that around the region and figure out what is the volume of that shape you get. The volume is mostly just an area, with the delta x contributing the thickness part of the volume. What is this shape? They call it a shell. They're about to call this the shell method. Did you guys used to eat the chips called combos? I'm always imagining a combos. Combos was a ship that was a tube. Usually it was pretzels full of peanut butter, but it's always some flavor of chip with some flavor of filling inside it. That's the thing I'm picturing when I do the shell method, is combos snacks. I feel like chip isn't even the right word either. How would I find the volume of this shell? What are the parameters going on here? My shell, let's draw a simpler shell, is going to have a height. It's going to have a thickness, which we will call delta x. And it's going to have two radii. I might want to think about the inner radius, or I might want to think about the outer radius. This is going to turn out to be one of those things that doesn't really matter in the integral. I'm going to call this inner radius r of x. I'll make it a lowercase r. Uh-oh. Oh, it was just this crashed. I think my stream is still going. It hasn't crashed in a while. That's a good sign. Man, this computer is getting better and better. I don't know. I feel like that is a real thing, where you break in your computer. Oh, I did not save. I don't have that saved. Dang. I'll give you another second. It's like the feeling of the more you use a new computer, it like starts acting better, which doesn't make any sense at all. It's definitely me who's getting better at using it. But I don't know what I'm doing differently that's making it not crash, but... Okay, this is a hard... Oh! Hey, it came back. Are we still... Is this the thing I was doing? Yeah, okay. So I was about to draw combos for the shell method. And I'm trying to imagine... given a specific shell with a larger thickness, so I'm better at drawing it, what is the volume of this shell going to be? What are the parameters I need to know? I need to know what is the height of this shell. I'll call that h. I need to know there are two radii going on. I'm going to measure the inner radius, although it doesn't really matter in the end. And then I've got the thickness of the shell, delta x. The volume of this shell, this is a cylinder with a cylindrical hole in the middle, is going to be the volume of the big cylinder minus the volume of the little cylinder. Right? The volume of a cylinder is height times base, right? It's the area of the bottom times the height of the thing. The area of the bottom is pi r squared and the height is h. So it's pi times hr squared. Our radius of this one is the inner radius plus delta x. So I'm going to label that little r plus delta x. Minus, what is the volume of the inner radius? The volume of the inner radius is just pi little r squared. No delta x helping that out. I FOIL this out. Oh, this one has an h on it too. I get pi h, if I factor that out, I now need r plus delta x squared minus r squared. I get pi h times r plus delta x is r squared plus 2r delta x plus delta x squared minus r squared. The r squareds cancel. I'm integrating 2 pi r h delta x plus pi h delta x squared. When I add these up, this part becomes an integral dx of 2 pi rh. Like the delta x becomes a dx when you take a limit going to an integral. Or that's what the dx is supposed to represent. This one becomes an integral of pi h dx. The dx goes to 0. This becomes an integral of 0. This goes away. The idea being a delta x squared becomes too small to even integrate against or something. Something like that. The thing goes away. I think maybe if I'd used the big radius instead of the little radius, this extra term wouldn't be there. But a delta x squared becomes insignificant as the thing goes to 0. We end up integrating 2 pi rh dx. There's other ways of getting there. I think maybe it's more useful for the shell method to picture, like when I'm trying to remember the formula for the shell method, I'm more likely to imagine it by taking my shell, a very thin thickness, I want to imagine cutting it. And unrolling it. I don't know how well I'm going to be able to draw this. Try flattening this out. Flattening it out won't completely work because the inner thing sort of is going to be too small and the outer thing is going to be too fat. But pretend you can unroll it anyway. And you will end up with a rectangle. What is the thickness of my rectangle? That came from here, was delta x. Not rectangle, rectangular prism. What is the height? This height becomes this dimension. And this dimension is the tricky one. It's either this length if I unrolled according to the outer one, or it's this length if I unrolled according to the inner one. Like we just said, it sort of doesn't matter which one you use. I think the correct one to use is halfway in between those two radii. But the distance around is going to be what was the distance around the shell. The inner and outer radii are close enough that it doesn't really make a difference. That radius is 2 pi r, is what was the circumference of the circle. So the total volume is length times width times height is 2 pi r times h times delta x. You add them up, turn it into an integral. You're integrating 2 pi r h dx. This is the formula for the shell method. So let's state these. The disk washer integral is pi integral from a to b r of x squared dx, or integral from a to b r of x squared minus little r of x squared dx. And they might be with respect to y. I have written them for x, but it could be a y integral if you're revolving around the other axis. The shell method is 2 pi rh. Or it could be an integral with respect to y. Let's try doing the same volumes we just did using the shell method now instead of the disk washer method. I like doing the same one two ways, because if I get the same answer, I know things went correctly. Oh, before I do that, I want to quickly think. Have you ever seen a wedding cake? Or, yeah, people have seen wedding cakes. You know how it's like a cylinder on top of a bigger cylinder on top of a bigger cylinder? I've always thought that it's kind of cute that the approximations you make from the disk washer method and the shell method are basically the exact same thing. The disk washer method looks at this cake and says, aha, I will cut you up into a disk on top of a disk on top of a disk. Right? I guess the idea is my real shape wasn't really a wedding cake, it was some other weird shape. And I approximated it by this wedding cake that I can cut into pieces that I know the area of. The shell method still approximate our weird blob by saying you're basically a wedding cake. I just build the wedding cake differently. Instead of saying a top layer and a middle layer and a bottom layer, I say you are a middle cylinder, plus a shorter, wider cylinder with a hole that I just pulled the innermost cylinder out of, plus a shortest, widest cylinder with an even bigger hole that I pulled both of those things out of. So like instead of building your cake, stacking it, you can build your cake by inserting things into tubes. You get the exact same shape. That is weird to me. They are the same approximation. They are giving us the same volume, but they come from trying to piece it together on the x-axis or piecing it together on the y-axis. Key thing about the disk washer method. If one of them was an x integral, the other is a y integral, and vice versa. So when I did the volume of a sphere of radius 3, SPH here, of radius 3, when I did it with the disk washer method, I thought about taking a horizontal line. To catch all of those horizontal lines, we had to go from y equals -3 to 3 and integrate something with respect to y. This horizontal line segment, when I swept it around the x-axis, gave me a disk. If I'm doing it with the shell method, it's going to be an integral along the other dimension. It's going to be an x integral. I want to think about taking a vertical line segment. How do I pick a vertical line segment? That means you are picking an x value. To catch all of those vertical line segments, you need to let the x go from the thing started at x equals 0, and the last point the thing exists at was x equals 3. So I'm going to be integrating something from 0 to 3 dx. What's the thing I need to integrate? Well, I need to find my r and I need to find my h. If I imagine my shell, my h is going to be this. It's going to be tricky to work out. What was my circle? My circle was x squared plus y squared equals 9. I'm going to need to again solve the equation of the circle. Last time we solved it for x, got x equals the square root of 9 minus y squared. This time I'm going to have to solve it for y. because I'm expecting my thing to be a function of x. I want to know for a given x value, what is the top of this line segment, what is the bottom of this line segment. The difference of those will give me the length of the top to bottom is the height of my shell. I solve this thing for y in terms of x. I get y equals square root 9 minus x squared, plus or minus. This time I don't throw away the plus or minus, because I have both the top one and the bottom one in my picture here. The top one is y equals root 9 minus x squared. The bottom one is y equals negative root 9 minus x squared. And the height is the distance from top to bottom is top root 9 minus x squared minus the bottom minus negative root 9 minus x squared. So my h of x comes out to be 2 root 9 minus x squared. What does my radius come out to be? My radius is this distance. Well, this thing was the x-axis, was x equals 0. And this thing was the x value that I picked, is x. My radius is the distance from 0 to x. My r of x is just x minus 0 equals x. Some books will tell you always use your radius is just x. I think that's misleading. That's a bad formula. If I was revolving about a different line, x equals negative 3, and this is x equals 0. So now when I pick my x value, I'm not going from x to 0, I'm going from x to negative 3, will be an x minus 3 as my radius. Your radius can be different. If you're revolving around the y-axis, the radius is just x. If you're revolving around a different vertical line, it'll be x plus or minus some constant. But it is always just a linear factor for the radius. Our integral becomes, we're integrating from 0 to 3, 2 pi, r of x, h of x dx is going to be 2 pi, integral 0 to 3, r of x is x, h of x is 2 root 9 minus x squared dx. That's the thing we want to integrate. Can we integrate this? That's 2 pi, I guess it's 4 pi if I pull out the other 2. Integral from 0 to 3, x, 9 minus x squared to the 1/2. This is begging for the u substitution. U equals 9 minus x squared, because the derivative of that is negative 2x dx is basically on the outside. I wish I had a negative 2 here. I'll divide by a negative 2 out there to fix that. I get negative 2 pi as my new constant out front. This becomes u to the 1/2. This and this and this combine to make just du, and I need new bounds of integration. My bottom bound is u equals 9 minus 0 squared is 9. My top bound is u equals 9 minus 3 squared is 0. So this goes u equals 9 to 0. This was x equals 0 to 3. We changed the integrand, we changed the differential, we changed the bounds of integration, we did the whole substitution. Hooray! We can now do this integral. What's the integral of u to the 1/2? It's u to the 3/2 with a 2/3 with a negative 2 pi also. And I need to evaluate that from 9 to 0. So I get negative 4 pi over 3. Plug in 0 minus plug in 9. 9 to the 3/2 is square root cubed. 3 cubed is 27. The negatives cancel, one of the 3's cancel. I get 4 pi times 9. I get 36 pi, which sure enough is the same answer we had before. Hooray! So we get the same answer with the shell method and the disk washer method. That's good to know. Let's do that other region also. Let me copy this problem. I've already drawn the region. Point. point, point. I got this shape. I got this line. I got the x-axis. So that's my region. We're revolving about the line y equals -2. This time we'll use the shell method. I should do this a little more clearly this time. A thing that students get really wrapped up around is, like, the first step you need to do is, should I be picturing a vertical segment or a horizontal segment? I like hanging all of my hats on, start with this vertical segment and then use that to draw all of the pictures around it. Should I start with a vertical or horizontal? The answer to that question is, do you get a disk or a shell when you sweep that around? If I pick this vertical segment, and imagine spinning that vertical segment around this axis, I'm going to end up with a washer. And I'm not trying to do the washer method, that's the thing we did last time. So instead I try taking a horizontal segment and sweep that around. That's the thing that gives me a shell. Cool. That's what I want. Picking a horizontal segment means picking a y value. To catch all of these horizontal segments, I need to let my y value go from 0 to 3. That will give me all of those, not 3, that top was at 2. 0 to 2 will catch all of those horizontal line segments. Good news, there's no phase shift. When we did this before, there were like two types of vertical segments. The type that went down to the x-axis and the type that went down to this line, which meant we had to cut the integral into two pieces. Here my horizontal segments stay the same as my y sweeps between 0 and 2. My left bound is always this function, my right bound is always this function. Cool. What are these functions? This function was y equals root x, but that was the form I used for the washer method. You do a couple of these problems, you get the hang of, you're always going to need to invert these functions to switch between a y integral and an x integral. This one was y equals root x before, it's going to be x equals y squared for us this time. This one was y equals x minus 2 before, now it's going to be x equals y plus 2. Because what I care about is I have picked a specific x value. To measure this distance, my height function, I need to say what is the difference between those two x coordinates. My height function is the right point minus the left point. What is the right to left distance? My right point was y plus 2. The x coordinate comes from the y coordinate by being y plus 2. It is a matter of y because I'm doing it for this specific orange segment, which comes from a y value that I don't know what the y value is. Minus what's my x coordinate? What's my left endpoint? My left endpoint was the curve x equals y squared. So your x coordinate is y squared. That's the height. How do I find the radius? The radius is the distance from here to here. Crud, I wrote this h of x, but this should be h of y. I know these are going to be functions of y because I've already written down that it's a y integral. What's my h of y and my r of y? Okay, I did my h of y. It's y plus 2 minus y squared. What's my r of y? This is the thing you're going to be tempted to say it's always y, but it's not always y, and this is a case where it's not. We're going from y down to -2. It's top minus bottom. The top thing is y, my bottom is -2. I get y plus 2. There's our integral. It's 2 pi integral of height times radius. Height is y plus 2 minus y squared. Radius is y plus 2. Calculus students who've learned how to do integrals will sometimes look at this thing and try and do some goofy, clever substitution. Don't feel the need to be clever. That's a polynomial. You know how to FOIL that thing out. Just FOIL it out and integrate the polynomial. What do you get when you FOIL it out? Y times -y squared will be -y cubed. How many y squareds do I get? Positive y squared minus 2y squared makes -y squared if I combine the like terms in my head. Positive 2y makes plus 4y, My constant term is 2 times 2 is 4. I did 1, 2, 3, 4, 5, 6 different products. 2 by 3 will be 6 different things. Cool. If you FOIL that out, this should be what you get. So this is 2 pi. I need to evaluate this integral. Negative 1/4 y to the 4th minus 1/3 y cubed plus 2y squared plus 4y. And now I need to plug in 0 and 2. And I only really need to plug in 2 because when I plug in 0, I'll get 0. Plug in 2. 2 to the 4 is 16. Divided by 4 is 4. I get negative 4. Minus 2 cubed is 8. Divided by 3 is 8/3. Plus 2 squared is 4. Times 2 is 8. 4 times 2 is 8. Minus plug in 0, you get 0. 8 and 8 is 16. Minus 4 is 12. I'm getting 2 pi times 12 minus 8/3. That's 2 pi times 36/3 minus 8/3. That's 2 pi times 28 over 3. 2 times 28 is 56. I'm getting 56 pi over 3, which is sure enough the same answer we got last time. I love it when they come out the same the first try. Hey, here's a warning. On the exam, I'm probably going to do the same setup where I say, hey, here's the one region. Do it once with the shell method. Do it once with the washer method. If you don't get the same answer the first time, don't stress too much over that. Like, showing me that you did your work clearly is so much more valuable than showing me that you added the fractions correctly. Like, there's a good chance that the reason you had a mistake was just adding the fractions. Don't get stuck in a loop where you waste the entire exam trying to figure out why the fractions added. Probably the mistake you made was adding the fractions wrong, and it is not worth spending an hour of exam time going back and figuring it out. But if you did get the same thing the first try, that is a good feeling of confidence you can use to slam out the rest of this. We just covered everything you need to do. Homework number. Do I still have the homework open? I don't think I do. Do I have it open here? You are not the right thing. Clear. Nope. Spring 2020. What? Courses. All courses. No. Current courses. Here's our course. This is our course, right? Summer 2020. No, this is my 111 course. I promise I know what I'm doing here. Here we go. Homework problems. You now have everything you need to go through. Problem 155. Heads up, I only put 3 problems about the shell washer method on the homework. They are 153, 154, 155. If that's not enough problems for you, your textbook probably has more. I feel like doing it 3 times is enough because it's not that complicated. If you're having a hard time with it, go grab more problems. I think this is mostly simple, so I didn't put that much. Feel free to stop this video. Go do those homework problems. I'm about to start talking about the last topic of the year, which is numerical integration, but you don't need to watch both parts right away. Go do some homework. Hey, you did the homework? Way to go. I'm going to start talking about numerical integration. This is another thing that could have been the first thing we talk about. I like saving it till the end because it's way easier. I like the last exam to not be the hardest exam. This last exam is the easiest exam by far. It's got a bunch of formulas in it, but you know, after the stuff you've been through, memorizing a couple formulas is not nearly as bad. Before I talk about numerical integration, I want to talk real quickly about average value. So the thing we're doing with numerical integration is we're going back to Riemann sums. If you're like me, Riemann sums were the worst thing from Cal 1, and you were very happy to learn the fundamental theorem of calculus and not have to think about Riemann sums anymore. A Riemann sum is that the integral of f of x dx, when you're trying to approximate an integral, you take the integral from a to b, you cut it into pieces. Usually they were equally width, but maybe they weren't. For each of these subintervals, you need to pick a point. Which point do you pick? That was a thing that was annoying. You could do a left-hand Riemann sum, or a right-hand Riemann sum, or maybe you did a midpoint Riemann sum once in a while. But you pick a point, and you call that point x star, and you add up the areas of these rectangles. Right. So the thing you were adding up was you took that x star value, you plugged it into the function, you multiplied it by the length of that subinterval. So this is xn star. That length of this interval is delta xn star. Usually they were all the same width, and you add them up and write. I've had it in my head for a while that thinking about an integral is a much harder concept than thinking about the average value. I think this is a thing you should have talked about in Cal 1. If you haven't, I'll explain it real quickly. The average value of a function on the interval is, to average a bunch of numbers, you add them up and then divide by how many numbers there are. To average a function, you want to add up all the function values, which is kind of what an integral does. But then dividing by how many numbers there are doesn't make sense because there were infinitely many numbers in there. You divide by how much numbers there were. You divide by the length of the interval. Part of the idea of the average value, it has like a really good visualization, is you're drawing a horizontal line segment so that the area that's too high exactly matches the area that's too low. Like if you've done the average value correctly, the part of the graph that's above the average value is exactly equal to the part of the graph that's below the average value. If you've ever gotten good at averaging numbers in your head, you sort of think about, this guy's too high, I'll cut 3 off of him and add him onto this guy who's too low. I sort of see where I get as I keep moving the high parts to fill in the low parts until you flatten everything out, and that's the average. This has a really good interpretation relative to Riemann sums, where instead of taking all the x values and multiplying them by these delta x's, like this is a really hard abstract thing to do. You pick a bunch of x values. How do you pick them? You want them to be sort of uniformly distributed. Maybe you're picking them at random. If you're picking them at random, it'll take longer to get close to the average. So maybe you pick evenly spaced ones instead. But the version of a Riemann sum would be to take those x values and average them. Take a whole bunch of numbers and averaging them is a way more intuitive, to me at least, thing than explaining multiply by the length of the interval and add them up. Like the averaging them has built in to I'll add them up and divide by how many there were, which was a thing that's part of every formula for doing a Riemann sum. So part of the assumption is here, now that these delta x's should be about equally width, if they're not equally width, then you're doing like a weighted average where if this guy's representing a very wide interval, then he should be more important to the average. He should be the final exam for averaging these things together. And this tiny skinny width is maybe your participation grade part of your average or whatever. This idea of averaging them takes a lot of the work out of a Riemann sum. This multiplying by delta x is a non-intuitive thing. Saying just average them is an intuitive thing. And the only thing you're off by is this 1 over b minus a. So the thing I want you to walk away from this slide is that 1 over b minus a of the integral is the average value of f. is approximated by averaging a bunch of f of x values in the interval from a to b. If those x values are more or less evenly distributed, then yeah. Which means if I multiply both sides of this by b minus a, the integral from a to b f of x dx is about the length of the interval times the average of a bunch of y values. And using the word average is nice because it bakes in a lot of the formula. We're going to have a bunch of formulas for computing some Riemann sums to approximate integrals. And the reason I'm emphasizing this is, like, there's these numbers out front of your thing that are a huge pain, and I think they're way easier to remember as it's always going to be the length of the interval times the average. Okay, let's get into these approximations first. When you talked about Riemann sums in Cal 1, you probably talked most about a left-hand Riemann sum and a right-hand Riemann sum. If I have an increasing function, the left-hand Riemann sum is always going to be an underestimate, right? If I think about these rectangles, which I wish I could draw them being the same height, a left-hand Riemann sum which comes from choosing to use the left endpoint of each of these subintervals as the height of the rectangle for that subinterval. The left-hand Riemann sum is an underestimate. An underestimate is sometimes called a lower sum. Estimate. And if I draw the same curve, the right-hand Riemann sum will always be an overestimate. The area of these rectangles will be bigger than the area under the curve. So the first of our three numerical integration approximation things is called the trapezoid rule. The idea of the trapezoid rule is, well, if I know for an increasing function one is an overestimate and one's an underestimate, why don't I split the difference? Let's average those two. For a decreasing function, the other one's the underestimate and the other one is the overestimate. Again, it's a good idea to average them. For a function that's sometimes increasing and sometimes decreasing, things are less clear, but usually you're increasing for a while and decreasing for a while, and still splitting the difference seems like a reasonable thing to do. The reason we call this the trapezoid rule is for any particular one of these subintervals, let's pick one closer to the edge where it's a little steeper. Using the left endpoint and the right endpoint and averaging them and saying that's my estimate for the value of the function is the same as finding the area of this trapezoid. If I connect the left endpoint and the right endpoint with a straight line segment, I'm basically finding the area of this trapezoid. Okay, so how do I write the trapezoid rule? Trapezoid rule says that the integral from a to b, f of x dx, is approximately T sub n, which we're going to call the nth trapezoid approximation, The nth is not the greatest word. Like, the thing that n is representing is the trapezoid rule on n subintervals. The n is representing, cut the interval b minus a into n pieces. Oh hey, I have a blank one over here. And I need to worry about making these pretty because I got the video going anyway. Yeah, let's try this out. The integral from a to b of f of x dx is about t sub n. This is the trapezoid rule. Cutting into n subintervals. You want to say it's using n values, but it's actually using n plus 1 values. Like, the thing that measures how complicated is it to use this estimate for the integral is how many times did I have to plug a number into the function. The nth trapezoid rule is, and we're plugging about n different numbers into the function, we're actually plugging in n plus 1. It's b minus a over 2n times y value plus y1 plus, 2y1, 2y2, 2y sub n minus 1, 1y sub n. The idea you're doing here is I cut the interval into n equal pieces. The left endpoint is a, the right endpoint is b. Cut the interval b minus a into n different pieces. The length of each piece will then be b minus a over n. So x naught equals a. x1 is a plus b minus a over n. x2 is a plus 2 b minus a over n. Down to xn minus 1 will be a plus n minus 1 b minus a over n. And the last one, xn, will be a plus n b minus a over n. Turns out to be n. The corresponding y values, y0 is going to be f of x0. y1 will be f of x1. yn will be f of xn. These formulas are a huge pain to write out, but most of the time they're not that bad because I just take my... I'm gonna hand you the interval from 1 to 3, and you're gonna cut it into 5 pieces, and now you have the specific numbers written down, and you never have to actually touch this stuff. But if I have to write out a formula for what these x values and y values are, this is where that formula comes from. The thing we're observing is that if this is y1, and this is y2, and this is y0, to get this trapezoid, I want to average y1 and y2. So y1 plus y2 over 2 is the thing I want to use when I'm adding this up. When I average these two, I'm going to have y0 plus y1 over 2. Well, hey, I used 2 copies of the y1. I'm going to end up with y0 over 2 plus a full y1 plus a full y2 plus a full yn minus 1, and using half of the last one. Like, the sort of the fundamental observation is, hey, this y value that came from the middle should be more important than this one that came from the end. The one that came from the end is sort of only representing half as much stuff as this guy. y1 is surrounded by y values that are relevant to my interval. y0 is only at the edge of the y values that are relevant to my interval. So he should be somehow less important. And instead of using all the y values equally, the one at the very left and the one at the very right should only be given half weight. Or maybe I'm averaging them or something. I don't know. You take this, you factor out the 1/2, you end up with this. The 1/2 is out here. These are the points. The reason I made a big deal about remembering the average value concept is that it sort of bakes into it this constant out front is like a annoying thing to have to remember. If I remember that the thing is always going to be b minus a times an average, the over 2n is all baked into there, because I can look at this and say, I use 1, 2, 2, 2, 2, 1. How many points got added up? I'm basically doing a weighted average where I'm saying everything in the middle counts twice, the ones at the end only count once. So use 2 copies of this number and only 1 copy of this number and this number, 2 copies of every other number. I'm adding up, if I count it up, 2n points total. So I added up 2n numbers, dividing by 2n makes this an average. So, pen, green pen. This part is an average, and then we multiply that by the length of the interval. And we're going to have 3 versions of this formula, and you can remember a good chunk of all of them as it's an average times the length of the interval. And that's what gives you the trapezoid rule. Alright, Cal 2 is the place where you advance, though, from just saying, here's an approximation of how good, here's an approximation for an interval. Cal 2, you want to be a grown-up and say, well, how good of an approximation is that? If it takes me 1,000,000 terms to get close, like if I don't know how good this approximation is, I don't know what to do with it, you know? So, there's a formula for how good is your approximation. I'm going to start a formula page where I'm going to put all the formulas. And then I'll end my YouTube video on that page so you can copy them down if you want. Here's a formula for the trapezoid rule. And the error estimate on the trapezoid rule is that the difference between the integral from a to b f of x dx minus t sub n in absolute values is no bigger than. It's no bigger than, there's a b minus a cubed, yeah. I'm not going to try and justify where this comes from, but it's b minus a cubed over 24n squared k2, where k2 is the maximum of the second derivative of the function on the interval from a to b. It's a similar deal as what we had for the Taylor series. To generate this formula, you think about what is the difference between, like you do the same thing that you did for the Taylor series. You take the second derivative, you integrate it twice, and you say that if the function was less than k2, what do I get if I integrate 0 over that interval? What do I get if I integrate this constant function k2 from a to b twice? You end up with a constant and then an x and then an x cubed, and this 24 shows up. And I'm not going to try and justify it. Your calculus textbook probably has a justification if you want to see one. This formula is kind of rough. Heads up, if I give you, when you see the practice exam that I post soon, there's a good chance it's up already by the time you're seeing this. I will give you this formula for the practice exam. I will not give you this formula. So the error estimates are a thing I will give you because they are a thing I have never wanted to have to memorize, so you don't have to memorize them either. But the idea of the trapezoid rule, the 1, 2, 2, 2, 2, 2, 2, 1 thing, is a thing you need to remember, and it's not that bad. Let's use the trapezoid rule to estimate Let's do the integral from... Let's make it 1 to 4 of 1 over x dx. This answer, by the way, is natural log 4. We're going to be estimating ln 4 by doing this. And let's do it with n equals 5. So the key thing is I take the interval from 1 to 4. I need to cut this into 5 pieces. That's an interval of length 3. Cutting it into 5 pieces, each piece will have a length of 3/5. So I need to go 1. 3/5 is 0.6, 1.6, 1.9, 2.2, 2.5. Am I doing this right? Nope, I can't add 6. 1.6 plus 0.6 will be 2.2, 2.8, 3.44. Cool. So I'm ending up with 6 values that I need to plug into my function. The trapezoid rule is going to be length of the interval is b minus a is 4 minus 1 divided by something, and when I do it, I don't figure out what that something is yet. The things I need to add up are 1 copy of plug the first number in. My function is 1 over x, so 1 over 1. 2 copies of plug in the second number, 1 over 1.6. 2 copies of 1 over the next number, 2.2. 2 copies of 1 over the next number, 2.8. 2 copies of 1 over the next number, 3.4. 2 copies of the 1 over the next number, 1 over 4. The thing I divide by is I want to think about it as to approximate the integral, I need to take the length of the interval times the average. Here's the length of the interval. I want to be averaging these y values. Oh, also I screwed up. There's only 1 copy of the last number. Is the whole point of the trapezoid rule. 2 of all the interior points, 1 of each of the edge points. How many numbers did I add up? 2, 4, 6, 8, plus 1 and 1 is 10. So adding these up and dividing by 10 makes an average. Multiply that by the length of the interval. Does this match up with what the formula said? It's supposed to be dividing by 2n. 2n is 10. Yes, this is the same thing. I'm showing you how I remember this formula. On the exam, this will be it. Put a box around this. For the homework, pull out a calculator and get some digits. Dear calculator. Quit. Hey calculator, just for reference, what's natural log 4? Hey calculator, what is 4 minus 1 is 3 divided by 10 times parenthesis. I like saying 2 times all these numbers first so I don't have to write 2 times a million times. 2 times, what are all the numbers that I'm taking 2 of? The reciprocal of 1.6 plus the reciprocal of 2.2 plus the reciprocal of 2.8 plus 3.4's reciprocal. So 2 of that. They all have the reciprocal on it. Cool. Plus 1 of that number is 1. Plus 1 of that number is 1/4. 1.41348. So the trapezoid rule gave us that natural log 4 is about 1.41348. Cool. The actual value was, I just had natural log 4 there, 1.386. We wound up with an upper estimate. We're not that far off though. We're only off by 0.03. The error, according to the trapezoid rule, the other half of the formula, this is the part I can never remember, is no more than b minus a cubed divided by 24n squared. 24n squared. Is this really a 24? I'm scared I'm messing this up. Ah, dang, I did mess it up. I wrote the wrong formula down first. Sorry. Hey! I hope you didn't put a box around this yet. This is a 12n squared, is the error on the trapezoid rule. It's the next one that has a 24. Our error is at most b minus a cubed over 12 n squared times k2. If I want to know how good this estimate is, which I do, find error was part of the problem. It was there the whole time. Our error is at most, I need to do this thing. The k2 is the hard part. The b minus a is the 4 minus 1 cubed is going to be 27 over 12. N squared is 25. How big is k2? K2 is the max of the second derivative. My function is x to the negative 1. Its derivative is negative x to the negative 2. Its second derivative is negative 2 x to the negative 3. Is 2 over x cubed. If I ask, what do you look like on 1 to 4? You are a decreasing function on 1 to 4. You have your max on the left at 1. I don't know why I'm shading it in. We're not doing this integral. So I can use k2 as 2. So our error is at most 4 minus 1 is 3. 3 cubed is, I'll just write 3 cubed times 2 over 12 times 25. 2 cancels with that and leaves 6. 6 cancels with one of those, leaving a 2. I'm getting 9 over 50. Is 18 out of 100 is 0.18. Our error is at most 0.18. We know that natural log 4 is 1.41, give or take 0.18. The actual error was significantly less than that. Our actual error was 0.03. So our actual error was only as big as a sixth of that. Yeah, that's about typical. The place that your max f double prime, the place where this k2 gets used is, what if the second derivative was as big as this the whole way? How far off would we be? So in general, like the amount you're off by is how exceptional is this point. Most of these points, 2 over x cubed is generally much, much smaller than 2. If I plug in, like, if I only go as far as 2, I'm already way, way smaller than 2. So that's why, that's the gap between the actual error and the perceived error. But anyway, there's the trapezoid rule we used to estimate that. Let's try the next rule. The next rule is dumb. The next rule is the midpoint rule. And this one doesn't really even deserve its own special name. The idea of the midpoint rule is, instead of using the left endpoint and the right endpoint, what happens if you just use the middle point? The way they write this midpoint rule is dumb. The integral from a to b f of x dx is about m sub n. M sub n, they write this as b minus a over n. They call this y 1/2 plus y 3/2 plus y sub 5/2 up through y sub, what is this, n minus a half. You take n point, the idea is those x values that we gave names to earlier, x0, x1, x2, xn minus 1, xn, we're inserting new x points in between. We call this x sub 1/2. We call this x sub 1.5. We call this x sub 5/2. It's the same concept before. X sub 1/2 is going to be a plus now half of b minus a over n. I'm moving half of a line segment over. The midpoint is just the midpoint of each subinterval. These formulas are a huge pain for the midpoint things. A plus 3 halves of b minus a over n. In general, x sub 2k plus 1 over 2 is a plus 2k plus 1 over 2 b minus a over n, and so on. And the y values are plug those in. Y 1/2 is f of x 1/2. This feels not clever enough to be worth its own formula. The reason that this is clever enough to be worth its own formula is when I try and approximate the error, which I will do the same way, except instead of approximating it with a straight line from 0 to 1, you approximate it by a straight line that's just horizontal through this point. And your straight line that is horizontal through this point, well, it didn't even have... How do you get the good estimate? I'm not going to pretend to try and come up with the formula why the error estimate is what it is. But the clever trick is instead of drawing the straight line from here to here, you say, well, if the function was doing something else, think about the midpoint. I don't need to think about a horizontal line through that midpoint. I will think about a horizontal line that has the same derivative as that endpoint. So now I'm thinking about a function that on this interval equals the same value and has the same derivative. You end up with a way better estimate than you think you should get. You end up with the midpoint rule error estimate is the integral from a to b f of x dx minus m sub n in absolute values is at most, the error is the same thing it was before but with the 24. B minus a cubed over 24n squared k2. Same k2. It's the maximum of the second derivative on the interval from a to b. It's the exact same formula but with the 24 on the bottom instead of 12. Which means that the midpoint rule is way more accurate than the trapezoid rule. The trapezoid rule, which had us being clever and saying, well, let's split the difference, like it's not a deep idea, but it's at least an idea, is just not as good as don't use these edge points at all. Just use the middle point of every interval and you get a better estimate. The midpoint rule is... So, let me copy all this to my formula page. And again, if I give you a formula that's asking you to use the error estimate on an exam, I will give you the error estimate formulas to use. But you need to remember what the midpoint rule is. And again, you can think of this as an average. There's n points in here, so adding them up and dividing by n is exactly taking an average. Take the average, multiply it by the length of the interval, that gives you the integral. Or it approximates the integral. Yeah, I forgot the absolute value here. It's the maximum of the absolute value of f double prime. Let's use the midpoint rule on the same estimate as before. So same problem, but this time let's use the midpoint rule and see if we actually get a smaller error. Same deal, I take the interval from 1 to 4 and cut it into 5 pieces. This one's going to be more of a hassle, because I'm going to need the midpoint of each of these things. I'm going from 1 to 1.6 to 2.2 to 2.8 to 3.4 to 4. But now I need to think about what is the midpoint of each of these. The midpoint of this is 1.3. The midpoint of this is 1.9. The midpoint of this is 2.5. The midpoint of this is 3.1. The midpoint of this is 3.7. That's halfway through each of these 5 pieces. I need to plug all of those into the function, add them up. So m sub 5 is going to be, plug all those in, 1.3 to the negative 1 plus 1.9 to the negative, or I'm not in my calculator yet, I don't need to write it the clever way. 1 over 2.5, 1 over 3.1, 1 over 3.7. It's the length of the interval is 4 minus 1, and then I want to, adding those 5 points up, I need to divide by 5 to turn it into an average, then multiply by the length of the interval. If I told you to do this on an exam, this is as far as you need to go. You don't need to plug the numbers in because you don't have a calculator for the exam, that's it. For the homework, I'm going to ask you to do it. Pull out a calculator, like, you got some time. You do gain learning from doing these estimates and seeing what the actual digits you get are. In this case, it's 4 minus 1 is 3, so I want 3 over 5 times 1.3 reciprocal plus 1.9 reciprocal plus 2.5 reciprocal plus 3.1 reciprocal plus 3.7 reciprocal. Boom, boom. You get 1.37303. How big is our error? The absolute value of our error is at most b minus a cubed over 24 n squared k2. K2 is the same before. I can use K2 is still 2 because the second derivative was like 2x to the negative 4 is at most 2 on the interval from 1 to 4. So this is going to be 3 cubed over 24 times 5 squared times 2 is, it's going to be the exact same error as we had last time, but half of it. It'll be 9 over 100. It's 0.09. Yeah, 3 cubed times 2 is 27 times 2 is 54 over 24 times 25. U reduced by 6, divide U by 6, I get 9, divide U by 6, I get 4, I get 9 over 100 is 0.09. So our answer is 1.37, give or take 0.09. The actual error is, if I ask for ln4 again, 0.01. Again, it's way smaller than, I guess it's 0.013. Again, it's about 1/6 of the original. That's probably coming from something about how far K2 is off from being 2 or something. Yeah. Right. So without knowing natural log 4, we're able to get that natural log 4 is about this, give or take 0.09. If I double the n value, then all of this is staying the same, except the n is getting doubled. That'll reduce the error by a factor of 4. So every time I double the number of points, I'm going to shrink the error by a factor of 4. I can make some estimates and figure out how big does my n need to get in order to know the error is at most this much. So I can answer some questions like that. We're going to have one more rule, but I want to observe something real quick. The ln4, the actual ln4 was, let's grab a new page. The actual retail value of ln4 is 1.38629. Do you guys actually watch The Price is Right? I like saying actual retail value from The Price is Right. I don't know if they even still make The Price is Right. Oh, that's right. It's got Drew Carey now. That's ln4. The midpoint estimate was 1.37303. Our error is negative 0.01326. All right, when we did the trapezoid rule estimate, we got a value of, I don't have it on my calculator anymore, 1.41348. 41348. 41348. And now our error was about, if I take this minus the actual value, why am I typing all this in? I can just type in ln4. Cut it off after a few digits. It's positive 0.02718. Okay. Observation 1. One of these errors was positive, one of these errors was negative. This is generally the thing that happens. If I imagine what's happening on one of these intervals, imagine this curve. I'm drawing something that's very concave up. And I'm imagining one of these tiny little intervals. The midpoint, the trapezoid rule comes from finding this area. If my function is concave up, it's not too hard to see that the trapezoid rule will always give an overestimate. The easy way of imagining what's going on with the midpoint rule is I'm using a rectangle whose height is this midpoint, but I'm allowed to tilt that midpoint to be, if I use the tangent line of the curve as the slope of my trapezoid that I use for the midpoint, I find that the midpoint rule, if the graph is concave up, then the graph will be bending upwards from its tangent line at the midpoint. The midpoint rule is giving me this value is the average of these two exterior values. It's still a trapezoid, but I don't care what the endpoints are. The midpoint is giving me the average of the things that I wanted. The midpoint rule is too low. I'm in a similar situation where one I know is too big and one I know is too small. If the thing is concave up. If the graph was concave down, the two things switch places. But again, I know that one is too big and I know that one is too small. Apparently somebody named Simpson noticed this. And I guess also noticed that, like, this is the after the fact version. I'm sure when Simpson was doing it, he was like, this is the terrible thing with math, is all the proofs you see are the best version of the proof that people have worked out after 100 years. The one that you figure out at the time is gross and ugly. I know that one is too big and I know that one is too small, and I also know the error estimate says that the midpoint rule is the better estimate than the other one, and the error estimate will be, like, the error is twice as big for the trapezoid rule as it is for the midpoint rule. And not only is the maximum possible error twice as big, the actual error tends to be twice as big. If I look at how far off these were, this 0.027 is just about double that 0.013. The error is just about double this. If I can predict that the error is going to be just about twice as much, which our error estimate computations show that it should be about twice as much, and doing it in practice, we find that it really is about twice as much. If I think that, like, think about this. If I have two estimates for a number, This one's too big, or too small. The little one is the too small one. This is the too big one. And I know that this is twice as close as that. It's not too hard to work out where is the actual value going to be. It's going to be 2/3 of the way from here to there. If the one that's too small is twice as far away as the one, then the actual number should be 2/3 of the way closer to the good estimate than it was to the bad estimate. This is called Simpson's rule. Simpson's rule comes from averaging the midpoint estimate and the trapezoid rule estimate using 2 copies of the good one and 1 copy of the bad one. So this is the origin, or this is a derivation of Simpson's rule. One way of getting there is compute both trapezoid and midpoint. Average them using 2 copies of the midpoint rule and 1 copy of the trapezoid rule. If I'm writing this formula, this is S sub, they call this S sub 2n. The reason we're calling it S sub 2n is the way of measuring how good your estimate is. You want to compare how much work to how many digits of accuracy. The amount of work that it takes to do the trapezoid rule and the midpoint rule are, for the midpoint rule, you need to plug n numbers into the function. For the trapezoid rule, you need to plug n plus 1 numbers into the function. But they're different numbers. If I'm doing both of these rules, I wound up using not just n plus 1, I wound up using 2n. I guess it's 2n plus 1. You end up needing to plug in twice as many numbers. Simpson's rule should be more accurate because it requires me to plug in twice as many points as the other 2 rules came from. But the formula for S2n would be, no one actually uses this formula. You use 1/3 of the trapezoid rule, the bad rule, 2/3 of the midpoint rule, the good rule. This isn't the way people write this out, though. The thing you end up doing when you do that, let me write this out, is they call this S sub 2n. It's b minus a divided by something. I never work out the something until I've done the other part. The thing you end up doing is I want to use 1 copy of y0. I'm going to use some copies of y1/2. And then I want to use 1 copy of y1. But the next copy of the interval is going to also use a copy of y1. So I'm getting 2 copies of y1 from the midpoint rule. You end up using 4 copies of the middle thing. It's 1 of this, 4 of this. The one here and the one here are the trapezoid rule. I wound up using 2 points. I want to use twice as many of the midpoint rule, which was my twice as good rule. I don't know if this is a useful way of remembering it, but it's 1, 4, 2, 4, 2, 4, 1. 4y sub 3 halves, 2y sub 2, 4y sub 5 halves, 2y sub 3, 4y sub n minus a half, 1y sub n is what goes in the Simpsons rule. If I work out how many points did I use, I had one of these groups of 1, 4, 1 represents one of the subintervals. So each subinterval wound up using 6 numbers added up. You divide by 6n. That's easier to do when you're doing a specific example. Did I write this down right? Yeah, it's 6n on bottom. Let's state Simpson's rule. Actually, yeah, this version was ugly. Let me write a nicer version for here. I should label this midpoint rule. This was trapezoid rule. This is the midpoint rule. And this one is Simpson's rule. Doesn't have a nice geometric interpretation. They call this S sub 2n, and it's b minus a over 6n. The numbers you put in are y0, 4y1 half, 2y1, 4y3 halves, dot dot dot, 4y sub n minus a half. Actually, let me start one step lower. 2 y sub n minus 1, 4 y sub n minus a half, 1 y sub n. So it's 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1 at the end. You have to end up cutting it into an even number of intervals for the 4s and the 2s to the pattern to line up correctly. Yeah. And what's the error estimate? The integral from a to b f of x dx minus s sub 2n is at most. The reason we go so far is to, like, we've gone like way deep into approximating things. Like, it felt in Cal 1 like there's no reason to actually do these Riemann sums because you immediately learned how to find the antiderivative and get the exact value. Who cares about these estimates? I'm hoping that you've remembered from our learning how to do integrals that there's lots of functions you can't actually find an antiderivative of. You can't integrate e to the x squared. If you want to estimate it, you're going to be doing something like this. So, like, and beyond that, the things that we actually want integrals of in applied purposes are very often things that came from making measurements. If I measure the temperature every second for 1,000 seconds, that's not a function I can find an antiderivative of. I'm going to be stuck doing some kind of computation to approximate the integral of that function, because I've only got the finitely many points. That would be a great application for Simpson's rule. And the reason we go so far is to say not just the trapezoid rule, not just the midpoint rule, we're also going to learn Simpson's rule, is because Simpson's rule is not so accurate. Doing twice as many points, like when we thought about the midpoint rule, doubling the number of points should give 1/4 of the error. Simpson's rule, the error is now it's b minus a to the 5th over, what's the number? 180 times 2n to the 4th. So it's not just an n squared anymore, it's an n to the 4th. This rule, when you double it, you aren't cutting the error down by 4, you're cutting the error down by 2 to the 4 is 16. Like, this thing is crazy more accurate. And the number that goes out here isn't K2, it's K4. K4 is the maximum of the 4th derivative. Cool. Let's try this out. And again, let's use it on our same integral that we've been estimating. We're going to use not the trapezoid rule, this time we're going to use the Simpson's rule. I don't call it the Simpson's rule. Use Simpson's rule to estimate integral from 1 to this with n equals 5. It is still n equals 5, but they're likely to phrase it as 2n equals 10. They tell you the 2n value for Simpson's rule to help emphasize that you're using twice as many points for Simpson's rule. So if I give you a Simpson's rule problem, I will tell you what 2n is. We're going to see that this is way, way more accurate than the other two rules. And it should be more accurate because I'm using twice as many points. But, yeah. What do we do? Excuse me. what do? We do the same thing, cutting the interval from 1 to 4 into 5 or 10 intervals. I'll count by 4 minus 1 over 10. Over 10 this time is 0.3, so I'm counting by 0.3s. 1.6, 1.9, 2.2, 2.5, 2.8, 3.1, 3.4, 3.7, 4. I want to plug all these numbers into the function and wrap them up in coefficients. It's going to be 4 minus 1 divided by something. What's my something? My something is how many points are getting added up, and I'll work that out after I've written the next part. I want to plug all these numbers into the function. I need 1 inverse, 1.3 inverse, 1.6 inverse, 1.9 inverse, 2.2 inverse. I didn't actually. 2.2 inverse, 2.5 inverse, 2.8 inverse, 3.1 inverse, 3.4 inverse. Oh, I screwed it up. No, I didn't. 3.7 inverse, 4 inverse, and I want to put the coefficients on. I want 1 of this, 2 of that. Nope, 1, 4. Let's put this in green. Save red for mistakes. I want 1 of this, 4 of this, 2 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 of this, 4 of this, 1 of this. How many points did I wind up adding up? If I count this, 1 plus 4 plus 2 plus 4 plus 2 plus 4, it's going to be, should be 30? Is that right? If I just count the 4s, 1, 2, 3, 4, 5 times 4 is 20, 22, 24, 26, 28, 29, 30. Yeah, we added up 30 function values. To turn this into an average, I want to divide by 30. It was 6n. Yes, 6n is 30, because n is 5. It's 3 times 2n. Yeah, some places don't write it as 6n, they write it as 3 times 2n on the bottom, which might be more valuable because you're looking at 2n as the number they gave you. I don't know, I just write 6n. I guess I'm doing that because I don't even think of it as 6n. I just think about it as what should I divide by to turn that into an average. If I ask my calculator, I get 3 over 30 times. I'm going to group all the 4 times, the things we have for. Actually, let me do the first one. We have 1 of 1 inverse. We have 1 of 4 inverse. We have 4 of a bunch of things. We have 4 of 1.3 inverse. And I'm grouping the 4 ofs together so I don't have to write 4 times a million times. 4 of 1.9 inverse. 4 of 2.5 inverse. 4 of 3.1 inverse. 4 of 3.7 inverse. And then we have 2 of a bunch of things. 2 times 1.6 inverse, 2.2 inverse, 2.8 inverse, 3.4 inverse. Close up the 2 ofs, close up the whole parenthesis. What do we get? 1.38652. So again, on the exam, if I asked you to use Simpson's rule, just write this. You don't have a calculator. You don't have to try and get digits, but it's fun to check the digits. This is fun with an asterisk. 1.38652. How big is our error? Our error is at most, it's b minus a to the 5th. This is bigger than the other ones. If b minus a is big anyway, it's bigger. But the bottom is way, way smaller. 180 times 2n to the 4th. Do I have this right? Did I write the... I'll just copy it then from my paper. It's 180, 2n to the fourth, and when I say to the fifth, k4. b minus a is 3, so that's 3 to the fifth on top. 2n is 10, 10 to the fourth on bottom. How big is k4? F is x to the negative 1, f prime is negative x to the negative 2, f double prime is positive 2x to the negative 3, f triple prime is negative 6x to the negative 4, f quadruple prime will be positive 24x to the negative 5. This is the function I want to know. How big are you on the interval from 1 to 4? X to the negative 5 is a decreasing thing. On the left you have a value of 24. That's the max. Max of the fourth derivative is 24. When you plug in 1, it's 24, and the function's decreasing. Right. I should know 1 over x to the fifth looks basically like this. From 1 to 4, it's decreasing. So that's what I use for k4, is 24. How much cancels? 180 is divisible by 9, so I can cancel 2 of those 3's. That'll be 27 over 20 times 10 to the 4 times 24. I guess I don't really... Yeah, whatever this is. Is there... Yeah, there's no joy in reduce. Well, let's cancel the 2. So I have 27 times 12 over 10 to the fifth. That's a 1 with 5 zeros after it. The fraction reduces more, but this is the thing I can write as a decimal. What's 27 times 12? 7 times 2 is 14, carry a 1, 7, 2, carry a 1. I think that's 324. No, it's not. What's 81 divided by 4? What? What? I got too old to multiply. What's 27 times 12? It is 324. I'm not too old to multiply. Hooray! Our error is give or take point. 324, move the decimal place back 5 times. 1, 2, 3, 4, 5. 0.00324 is what we know our error is at most as bad as. What did we know it was as bad as before? Using the midpoint rule, we got the error was at most 0.02. It's not really fair to compare this 0.003 to that 0.02, because this Simpson's rule, we had to do twice as much work. We had to evaluate twice as many points. We had to make twice as many measurements to get this better error estimate. The more fair comparison would be to compare it to, well, what would my midpoint estimate be if I took twice as many points? And we just made a big deal about taking twice as many points will cut the error by a factor of 4. If I divide this by 4, 27 divided by 4 is about 0.006. We would have an error of about 0.006. Simpson's rule is giving us an error of 0.003. It's half as much for this interval. Part of the issue here is this b minus a value is big. If I took even a slightly bigger error, n value, it's really easy to see how this is going to get, the bottom of this has an n to the 4. It's going to get bigger way faster than the other. So for this particular bad value of n, Simpson's rule's only giving us, it's still giving us profit, but only a little bit of profit. The thing try to emphasize is if you pick a slightly bigger n value, like doubling or tripling the n's, your returns are so much bigger on Simpson's rule than they are for the midpoint or the trapezoid rule. So it's 0.00324 is our estimate on the error. I'm wondering if the real error is even smaller than that. Hey calculator, what's ln4? Oh wait. Let me hit second enter. Second enter. So this was what the Simpson's rule estimate is. If I subtract ln4 from that, 2.258 e negative 4. Our actual error is 2.2 e negative 4 is move the decimal place back 4 times, so that's 1, 2, 3, 4, 0.00022. Really? Did I do this right? Okay, calculator, what is ln 4? 1.3865, we had 1.3862, yeah, we're off by 0.00022. Ah, cool. So we're less than 1/10 of the error. It was about 1/6 of the error before, now we're down to, is that maybe a 12th? Cool. Why do I have 2 things for the error? This is what the error turned out to really be. The Simpsons rule tells me the error is no more than this. The real error is this, which is yes, no more than that. Knowing the real error is a luxury you get to figure out after the fact because you knew what the value was without Simpsons rule. Like, this is a thing I can tell because I have a calculator to tell me what natural log 4 is. The whole point of Simpsons rule is to estimate things that you don't have all the digits of. But we do it on the other ones anyway. I want to do one more example with Simpsons rule to show off a goofy fun fact. Example, let's use Simpsons rule. To estimate let's do the integral from 1 to 3 of x cubed. Let's only use 2n equals 2. Find and abound on the error. Uh, 2n equals 2 is really easy. So I'm taking the interval from 1 to 3, cutting it into 2n equals 2 equal pieces. I get 1, 2, 3 are my values. Simpsons rule, s sub 2, is going to be length of the interval is 3 minus 1, divided by something. I like to figure out the something afterwards. I want 1 of the first value, 4 of the second value, 1 of the last value. It would be 1, 4, 2, 4, 2, 4, 2, 4, 1, but we're already done, so we have the 1 at the very end. How many numbers did we add up? 1 plus 4 plus 1 is 6, so to turn that to an average I need to divide by 6, and then multiply that by the length of the interval. My S2 is 2 over 6, f of 1, my function is x cubed, so it'll be 1 cubed, 4 times 2 cubed, 1 times 3 cubed. I'm getting it's 1/3 of 1 plus 2 cubed is 8 times 4 is 32 plus 27. 27 plus 32 is 59 plus that 1 is 60. I'm getting 1/3 of 60. Our estimate is 20. How bad could our error be? Our error is at most what is it? It's b minus a to the 5th. That's going to be pretty big. Over 180 times 2n to the 4th. That's not going to be that big because we didn't even use that big of an n. Times k4. b minus a is 3 minus 1 is 2. 2 to the 5th. So we're off by as much as 32. Divided by 180 times 2n is 2. 2 to the 4th. Oh, those will cancel. To leave just a 2, 2 over 180. So it's only 1/90th of k4. How big is k4? Our function is x cubed. Our derivative is 3x squared. Our second derivative is 6x. Our third derivative is 6. Our fourth derivative, the one we want the maximum of, is 0. What? It's 0? We're off by at most 1/90th of 0. When you take a cubic polynomial, its fourth derivative is 0. And anything up to cubic. Like if you have a quadratic or a linear or, some gross cubic, because its fourth derivative is 0, Simpson's rule is automatically giving you exact values. So we're getting that the integral from 1 to 3 of x cubed dx is 20, give or take an error of 0. It is 20 exactly. Simpson's rule can give you exact values. This is pretty cool to estimate, or to evaluate, the integral of a cubic function. If I want the integral from 1 to 5 of x cubed minus 6x squared plus 2x plus 8, well, that's going to be length of the interval divided by f of 1 plus f of 3 plus f of 5. Oh, I need 4 of this. Divide that by 6. This may be easier to work out than the integral. I don't know. But for any cubic, you can evaluate the integral by plugging in those 4 points, averaging them with the 1, 4, 1 weights, and then multiplying by the length of the interval. That's kind of a cool trick to be able to do. I guess I should check that the trick actually worked by doing the integral. If I integrate x cubed from 1 to 3, it's 1/4 x to the 4 evaluated from 1 to the 3. That's 1/4 of 3 to the 4th is 81, 1 to the 4th is 1. 1/4 of 80 is, sure enough, actually 20. The fact that Simpson's rule lets you integrate a cubic immediately is pretty cute. And you can sort of think about like the midpoint rule. Okay, the trapezoid rule is saying let's draw a straight line and figure out that integral. The midpoint rule, you can think about, I will look at that point and think about the slope and use that. This is very close to the function. What Simpson's rule is doing is taking a cubic polynomial which has the right value here, the right value here, the right value here, and the right slope here. If I try to figure out what is the function that goes through this point, has this slope, goes through this point, and goes through this point, there's only one cubic function that does it. The fact that you've got so many points that you've harnessed is giving you a really accurate estimate. And that's what Simpson's rule does. You can actually tell Simpson's rule to just do a quadratic, and you get the cubic approximation out for free. Like if you didn't ask the slope to be it, you will get the same integral as if the slope was it, because something, something, symmetry, something. That's it. That's all the homework. That means all the lecture, and Cal 2. This is all the topics we're going to talk about. I'm probably going to lecture over a couple more extra things that won't be in the homework, or maybe... am I going to give you a project? I don't know. We're skipping... Yeah, no project, but I'll make you watch some stuff about Fourier series. Hey, here's the homework. You've got everything you need to do all the homework. I'm going to post a practice exam after I'm done with this. Yeah, there's only... Was it like just 2 problems? I gave you 2 problems about the Simpsons rule and the midpoint rule and all this junk. But, oh man, the 158, I did the exact problem from 158. Well, you do it with the midpoint rule and the trapezoid rule. But yeah, that's everything you need for all the homework. I should clarify when doing this that, so for 157 I gave you the delta x, not the n. Delta x is what you think it is when you're doing the midpoint rule and trapezoid rule. Delta x is the distance between 2 consecutive values. When you're doing Simpson's rule, the delta x becomes vaguer. Like, I am never clear on whether delta x is supposed to be half of what it is, or double what it is, or what. For the midpoint rule and the trapezoid rule, though, what is delta x is clear. I think I will avoid using the delta x notation when I tell you to do Simpson's rule. Done with lecture. I'm going to post a practice exam. Sometime during the week I will do the practice exam. I think we should be ready to have the exam on Friday. And and we can spend next week on a retake or getting ready for the final. I think I've told each of you this by text. You're allowed to, or by email. I'm gonna let you retake one of the 3 regular exams the last week of class. Okay, let me talk about calendar stuff. We have a week that ends the 19th. We have a week that ends the 26th. I want to put exam 3 this coming Friday. You got a week to finish the homework. That seems like plenty of time. This is way easier than last semester's stuff. The following Friday, you can retake any one exam. Let me double check that I know when our final is. I think our final is the Wednesday after that, but I should look that up. Is it more important to run faster or run longer? Whatever. USCL exam schedule. SC.edu. Well, you don't have anything useful. Let's try you. Summer 2020 final exams. Our class. That's not. Is this our session? Did we start May 11th? No, we didn't start in May. I have no idea when our final is. I'll figure that. You don't need to watch me figure out what the final is. These dates might be wrong. I need to figure out when the final is. I hope it doesn't turn out our final is in like 4 days and I'm not ready for it. I'll text you or email you or whatever. I'm going to stop streaming now. Before I stop streaming, let me pull up the... Hey, here's the big formula page for trapezoid rule, midpoint rule, Simpson's rule. If I give you an exam, it will include this statement and this statement and this statement if I ask you to use the error estimates for these rules, which I'm likely to put on the exam, because we haven't covered that much stuff. Okay, I'm done talking now.